Hello class, this is Mr. Hart, and in this podcast we want to start the unit on voltage. And voltage is something you probably have heard before with describing like batteries, for example. A 9-volt battery is a common type of battery, or a 12-volt power source, or a 120-volt wall outlet, or something like that, right? So we hear the word volts a lot, and it's kind of our way of describing potential energy in electricity, okay? But let's kind of get to how we calculate it first and how we define it before we get into those other applications, okay? So if we look at voltage and we look at the vocabulary, let's first of all remind ourselves that electric field is that strength and direction of the electric force in any given area, okay? We talked about that last lesson. And then the voltage is the potential energy difference between 2 points in that electric field, okay? So we can kind of look at the force strength between 2 points and say, well, this area is much stronger than that area, or the particle or charge would push harder on this area than it would in that area, okay? But a voltage is a way of describing not the force, but the potential energy difference between 2 points, okay? And so if we want to calculate it, it is actually not a very difficult calculation to do. The voltage is simply equal to K times Q over R. So if we look at the different symbols, capital V is a little confusing because it represents voltage when it's a symbol, but it also represents volts when it's a unit. Okay, we'll see that in a second. Okay, and then K, of course, is Coulomb's constant. And you still use the exact same value. Q is charge of the particle creating the field. And then R is the radius or distance, right? But let's take a look at units really quick. Okay, if you recall, Coulomb's constant was measured in newtons meters squared per coulomb squared. Okay, and then charge is obviously in coulombs. And then radius is in meters, okay? So you cancel those out and you end up that voltage is measured in newtons with 1 meter canceling out, so Newton meters per coulomb, okay? 1 coulomb cancels out, right? And so meters, coulombs, right? So Newton meters per coulomb. And that is what we describe as V or volts. Okay, so it's again really confusing because when it's in the equation, it's voltage, but it can also be described as a unit. So a 3-volt battery, for example, is a 3 Newton meter per coulomb battery. Okay, so we'll see this is kind of tricky. We can say the voltage equals 3 volts. Okay, I think that's kind of poor convention, but hopefully that makes sense. Okay, but voltage will be measured in volts. Okay, and it means Newton meters per coulomb. Okay, let's just do an example problem and you can kind of see how this works out. Okay, so what is the voltage 6 meters away from a positive 1C charge? Okay, or basically what's the potential energy difference between the charge and a distance 6 meters away from it? Okay, so if we say, well, we know the distance, or R, is 6 meters, right? The charge, Q, is 1 coulomb. Then we get that the voltage equals K Q over R, which is equal to K times 1 over 6, okay? Or 1/6 of K, and K is 8.988 times 10 to the 9th, okay? And so times 1 over 6. And then when you times that out on your calculator, 0.988 times 10 to the 9th times 1/6, you get that it's equal to 1.498 times 10 to the 9th, okay, volts. Okay. So again, usually you won't see charges this big, right? You won't see 1 coulomb charges, so you won't see a 1 billion volt power source, right? But that's the voltage. So you can say V equals 1.498 times 10 to the 9th volts. Okay, and this is where it gets confusing because this is V, the symbol. to represent voltage, this is V, the unit, okay? So don't get those confused, okay? This is the symbol that represents voltage as a quantity, and this is the unit that represents a Newton meter over Coulomb, okay? So just be aware of that as you're going through. It can be a little tricky to think about sometimes, but that's the same. They're the same letter, right? But they mean different things, okay? Alrighty. Let's do one more calculation. So try this one on your own really quick. So what is the voltage 2 meters away from a negative 3 Coulomb charge? Okay. And so if you plug that into the equation, voltage equals KQR, you get that the voltage 2 meters away and 3 coulombs. And again, this is a negative 3 Coulomb charge, so we put negative 3 over 2 times that by 8.988 times 10 to the 9th. And when you put that in your calculator, you get that's negative 1.348 times 10 to the 10th volts. Okay? And so that's the voltage. Okay? And again, not the same as the symbol. Okay? And just like with force, the negative sign means that the particle will want to move towards the charge, right? This is again for the electric field, so it's always for a positive particle. So if there's a negative charge present, it's going to want to move towards the charge. Okay, but that is our voltage. Alrighty, so we can calculate this value, but let's think conceptually about why it's such a powerful quantity to be able to describe. Okay, and one of the most powerful applications of voltage or thinking about voltage is with batteries. Okay. And so if you hear about batteries, you probably know that their power is often described in terms of voltage, okay, or their capabilities, I should say. So for example, a AA battery is 1.5 volts, okay? And then if you have two batteries in a electronic device, okay, that makes it a 3-volt battery. They add together, okay, to make it 3 volts. But what does that mean? Okay, what does that voltage difference mean? It means that if I connect or look at the charge buildup basically between this side of the battery and this side of the battery on the back, okay, there's a 1.5 volt difference, or basically the potential energy difference is 1.5 volts, okay. Think of it as like a hill, okay. If you're thinking about gravity and potential energy, right, you could say, well, if the hill's 10 meters tall, okay, then it has such and such potential energy associated with it compared to the ground, okay? You take the difference in heights, times it by 9.8, okay? And you can say, well, that's the potential energy difference between those 2 points, okay? Exact same thing with the battery, okay? Basically, if I hook something up between this point and that point, there's this much energy that it will be capable of providing, right? So small objects, or small electronics I should say, don't require a whole lot of energy, so they can be powered by AA batteries because that 1.5 volt difference is enough to have the electrons flow from here to the other side, okay? But in comparison, you won't be able to power your TV with AA batteries because it needs a much larger potential difference in order to make it work, right? But that's what they're doing when they describe these batteries and make these batteries, right? They're telling you how much of an energy difference you have between this point and this point, so that when you hook up the circuit, you'll be able to see or be able to make it work based on how much voltage you have available. How steep is that hill, basically, or how high is that hill, I should say, okay? How much energy is available to be used, okay? And so voltage is very useful for designing circuits, okay? A lot of specifications are based on how much voltage a circuit needs or electronic needs, okay? And when we get to the circuits unit, you'll see why voltage is such a useful way of describing this, okay? Alrighty. And while we're on the topic of batteries, let's go through a little bit of the history of batteries. It's kind of a cool thing to think about, okay? And batteries are very historically used. They're actually the first way that we actually made electricity, okay? And it came from what were known as Leyden jars, okay? So Leyden jars, basically what they would do is they would take these jars and fill them with certain chemicals. And what would happen is when the chemicals would mix together, basically, they would build up electric charge. They would ionize and put electric charge on the outside of the jar. And so they'd stick this, or I should say in the solution, they'd stick this metal rod on the outside of the jar that would go into the solution, and then it'd make these electric shocks or electric discharges that would occur. And so they'd see these little lines, right? We know it's electric discharge now, but that's when they first discovered electricity. Is they'd see that this fluid, right, this solution they had made, would shoot out these little sparks when it touched metal. Okay, that's what's known as a Leyden jar. Okay, they'd build up electric charge from the chemicals. Okay, and then they'd shoot it out at things, basically. Okay, and that's how they discovered electricity. All right, and so that was actually one of the first ways they were able to do it. Another way that came on early on was static generators. So kind of the idea of rubbing your socks against the floor, right? We've all done it before. We talked about this with electric discharge. You rub your socks on the floor, it builds up that charge, and then you can touch the doorknob and it shocks you. Okay, well, they do it on a much grander scale, and they'd make these big belts, and they'd rotate, and they'd get this charge building up on these metal tubes, and they could see these huge sparks flying to the other side. Okay, so that was also a very common way to build up electricity. Okay, and they get bigger and bigger, and you get these huge generators, and they'd bring them to fairs and shows, and it was just kind of a new and exciting thing to see electricity, right? And so they'd bring them to these shows and show off these sparks that were flying off to audiences, and it was kind of a big thing. But again, they had no idea what was going on at the time. It was just kind of a new phenomenon. It wasn't until people like Michael Faraday and others that were able to kind of describe what's going on with the electrons and why they're flowing and things like that. Okay. But one of the biggest discoveries that happened with electricity, okay, came when a man by the name of Galvani, okay, was experimenting with dissected frogs, and basically realized that when you put an electric charge through, or electric flow basically through frogs' legs, they would pop up, okay, or flinch basically. And it's kind of a morbid experiment if you think about it. But basically what it was showing is that the nervous system actually depends on electrons flowing, okay? And when that's how our body interacts, that's how we're able to move, is, you send electrons and other, pulses through your body, and that tells your nerves and other things how to move and respond and react, okay? And Galvani was one of the first people to be able to discover that, okay? And, you just basically shock frog legs and show that they would move and that things would tighten up and things like that. And that's how the nervous system worked, okay? Alrighty, so that's kind of the history of electricity and batteries and that type of stuff. Let's get to the guy that really made batteries something that was useful and practical. And what do you know? It's Alessandro Volta himself. Okay, it was kind of the father of batteries and electricity in that sense. Okay, which is why it's called the volt and voltage, right? If you discover something cool like that, then you name it after yourself, right? That's how physics works. Okay, but Volta was the first one to build kind of these large batteries that were controllable. Leyden jars were kind of dangerous because you couldn't really control when the charge moved. Okay, but Volta was kind of able to make these insulated batteries that you could hook up when you needed to use the charge. Okay, and one of the first batteries he made was called a voltaic stack. Okay, is what they call it. And basically you put layers of copper and zinc alternating on top of each other. Okay, and because they ionize at different charges, I believe copper ionizes positively and zinc ionizes negatively, you could put these stacks together, and when they would ionize, you get this huge charge building up on the voltaic stack. Okay, and then you put them in these big jars and these other containers. You could put them linearly like this guy shows. You can, if you kind of look closely, you can see them kind of inserted into that wooden stack right there. And then you'd make these voltaic piles or voltaic stacks, and they'd give electric charge. Okay, just kind of like our modern batteries today, right? You'd have a positive voltage and a negative voltage. Okay, except these are much larger, and you could generate electricity from this. Okay, so that's some of the first battery designs. Okay, here's a closer look at a voltaic stack or voltaic plates, voltaic pile, whatever you want to call them. Okay, excuse me, it was silver, not copper. But basically, you put a copper plate, or sorry, silver plate or zinc plate, put some insulation between them, put another plate, then the next plate, put some insulation between them, and basically they'd ionize in different ways, and you just get this huge charge that would build up between them. Okay, and the more of these voltaic piles, they'd call them, that you had, the bigger voltage you'd have in the battery. Okay. Alrighty, so that was kind of the first batteries that they made, and then they realized that we can make them smaller if we use solutions. Okay, you probably have heard of like battery acid. Okay, so our modern batteries nowadays don't use these piles; they use acid and other things. Basically, you got a insulated material between the outside and the inside of the battery, and then on the inside you have a certain solution or acid that ionizes positively, right? And you stick that to the top end of the battery, and then on the outside you have this insulated material, and then you have just kind of a solution that ionizes negatively, and so you get negative charge buildup, and then when you connect the two sides you get electron flow occurring. Okay. And so the reason batteries eventually die off, right, is this solution can't ionize positively forever. Eventually all the charge will be taken and gone to the other side. And so then once that's occurred, then the battery's neutral. It can no longer provide any electricity because it doesn't have a voltage difference. Okay, so that voltage difference slowly gets eaten up between the positive cell and the negative cell. But again, you just have those two solutions that are those positive and negative charges basically. And you put them inside the battery, and then when you connect them, the charges flow from one end to the other. Okay. Alrighty. And then another common thing for batteries is making solution baths. So this is for like car batteries, and you've probably seen these where they put these plates down into a solution. Okay, so think of like a car battery. And so the common way is to put like a zinc plate and a copper plate inside of a solution. Okay, and then what happens is if you put them in the right solutions, zinc, if I recall correctly, ionizes negatively. Okay, makes the solution negative. Okay, and then copper ionizes positively, makes the solution positive. Okay, and so then again electricity can flow. You got a voltage difference between these two. Electrons flow to the copper plate, if I'm recalling correctly, and you get this flow of electrons through the wire, which can power a light bulb or something like that. So what your car battery does is you have this solution, this battery acid as they call it, and then you stick a whole bunch of these plates in a row, and then you can get this huge voltage buildup that you use to power your car. Okay. And then under that same idea, that's how like a fruit battery works. Okay. You probably have heard of like a potato battery running a clock or something like that. Okay, it's kind of a common science fair experiment. But again, it works the same way. You put it in some type of fruit like a lemon. Usually it's like a zinc nail and a copper penny. Okay, and when you stick those in, you get the negative charge building up on the zinc and the positive charge building up on the copper. So then if you connected a light bulb or a clock to it, right? Let's say this is a light bulb. Okay, and the light bulb will glow, right? Because, electrons are flowing through the light bulb to the copper, and that's what's ionizing it. Okay, so the property of the metal itself ionizes certain solutions, okay, certain acids. So fruits and potatoes often have those solutions, and so the zinc can just ionize and the copper can ionize, and then you can get this electron flow. Okay, alrighty. So again, kind of a lot of the history, but just realize, right, the whole point of this lesson is that in order to have a battery that works, okay, these batteries that we know, AA's, 9 volts, car batteries, right, you have to be able to build some type of voltage difference. Okay, if you can build some voltage difference from ionizing solutions or something like that, then it works out. Okay, but there you go. So this is kind of a fun homework. It's a lot of conceptual questions and thinking about voltage and things like that, but just make sure you do that, and let me know if you have any questions, and thank you for watching.